And welcome back, AP Calc students. I just wanted to go over some derivative graphs, and I'm hoping this is something you can copy and have as a part of your notes for the exam. But I've gone over this in most of the review videos whenever it's been a derivative graph, but it's nice to just have this by itself. So I just want to go over the original function versus the derivative and the second derivative, and peaks and valleys, flat spots, that type of thing. So I'm going to see if I can draw 3 graphs here, actually. And I think I have enough room I can draw these. So the first one is just the classic graph that I like to have that tells you most things you need to know, and it's a good one to have. And I like to always start with just a general cubic function, and that will make it nice and simple. And you just start here and make your x-axis nice and low, hopefully level. Running out of ink here. Okay, and then what we're going to do is just do our approach of peaks and valleys and handcuffing, all that stuff here. So this is our x-axis here, and this is f. All right. So I'm going to switch to red, and we're going to do our handcuffing. Okay. So when we do the handcuffing, you just remember, you always go to peaks and valleys because it's all about the slope of the tangent. Now, this is the original function. I'm going to handcuff the valley bottom to the x-axis because the slope of my tangent is 0. So the graph of my tangent, which is the graph of the derivative, which is the slope of the tangent, will be 0. So it's going to cross the x-axis there. I'm going to handcuff the peak to the x-axis because the slope of the tangent is 0. Slope of the tangent is the derivative, so the graph of the derivative has got to cross the x-axis here. And this is all about increasing and decreasing. So now I just say the original function is increasing. That means the slopes of all those tangents were positive. Or the graph of the derivative has got to be above the x-axis because the function is increasing. Now, between the handcuffs, the original function is decreasing, therefore the graph of the derivative has to be negative. Okay, now don't worry about how far this comes down, it's not important, but you just know that I have to get from 0 back to 0, but I have to be below the x-axis, so I'm just negative, I'm below the x-axis. Now from the second handcuff onward, we're increasing, and so I'm just above the x-axis, and that's the first derivative, okay? And little subtleties here where it's crossing and stuff, not important, okay? Then the next thing I want to do, I want to switch to blue to graph my second derivative. So I treat the original function, treat the derivative like an original function, and then I just do what I just did. So this is the red function here, just has one valley bottom right there, and I'm going to connect that to the x-axis. Okay, because the slope of this tangent is 0, so its derivative is going to have to cross right there. The red function is decreasing, therefore the graph of its derivative has got to be negative. The red function is increasing, therefore the graph of its derivative has got to be positive. And there is its second derivative. Now, you originally learned that second derivatives tell us about concavity, which is true. So the x-intercept, or the 0 of my second derivative, is corresponding to an inflection point, if I graphed halfway decent here. Okay? And there's all sorts of information now you want to use to look at this that can help you. Okay? Now, the first thing is, when you're learning, oftentimes we focus on all 3 graphs, but sometimes the third graph, the second derivative, can actually be a little bit confusing, and in most AP questions, they only give you the red graph. And the red graph has to tell you everything you need to know, and it does once you've done enough of these. So here's what I want to show you. Let's look at what's going on here with the concavity here. So if you look at the original function is concave down wherever blue is below the x-axis. So second derivative negative, original function concave down. Second derivative positive, original function concave up. But instead of looking at the second derivative, you want to get used to looking at the first derivative. So when the first derivative was decreasing, that's how we figured out where blue was going to be negative. So you can just skip that step and you say, well, wherever the first derivative is decreasing, the original had to be concave down. Wherever the first derivative was increasing, the original had to be concave up. That allows you to not actually need the second derivative. But the thing you don't want to confuse is you still have to worry about positive and negative of the first derivative. Where's the original increasing? Where the graph of the derivative was positive. Where's the original decreasing? The graph of the first derivative is negative. Original function increasing again, graph of the derivative is positive. So I always like to have this one handy that you can always just, if you're getting confused, you can clarify. And so you want to have this three colors ready to go here. The red, blue, and black. Okay. What I want to do is do the same graph again, but all I'm going to do is actually eliminate the blue graph and see what we get here. Okay, so I redrew the original function here just so we could look at it again, so I want to show you a slightly different approach here. And before I continue, I did want to show you some summaries down here that I was saying. So again, if you'll notice, where the derivative is negative, so where first derivative is negative, the original function is decreasing. Okay, where the first derivative is positive, okay, the original function must have been increasing, and you'll see that correlation there. Where the first derivative is decreasing, wherever it is decreasing, the original function is concave down. And where the first derivative is increasing, the original function is concave up. Now, if you'll notice, I didn't write anything about the relationship of the second derivative to the first derivative because it's not necessary, and you want to, if you can, kind of wean yourself off of that. Okay, so for this next graph here, I'm basically going to just do the same thing, but I'm just going to see if we can get all of our conclusions without using blue. Okay, and I'm going to add one other thing here. So I would go to this and I would say, okay, I'm getting the hang of this here. I'm going to handcuff there, and I'm going to handcuff here. And I know that those are my x-intercepts of my first derivative because the slopes of my tangents are 0. A derivative is the slope of the tangent, so the graph of the derivative's got to go through there. My original function is increasing. The graph of my derivative has got to be positive. My original function is decreasing. Graph of my derivative is going to be negative. Original function is increasing. Graph of my derivative needs to be positive or above the x-axis. Okay? Now, I'm not going to graph blue on purpose because I want to point out something else that's going on here. Frequently, they're going to ask you about where is the inflection point on the original function, and all you have is the derivative. Now, you could go this way and try to get the inflection point this way, but I want to show you another method. If you want to look for the inflection point on the original function, you go to the peaks and valleys of the first derivative. So I'm going to go to the minimum. All I have is a valley bottom here. I'm going to go to here, and I'm actually going to switch to blue because just to make it distinct here so we don't get confused. I'm going to go to this little minimum right here, and I'm going to say, well, that's going to give me my inflection point. And I had no need to draw the second derivative. And in fact, I'm going to add a second thing here. Okay, and I'm going to apply what's down here. Where the first derivative is decreasing, notice the first derivative is decreasing, the original function is concave down. Clearly it is, and in fact that minimum gave me my inflection point. Where the original function, or where the first derivative is increasing, the original function is concave up, and sure enough it is. So you can get all of your concavity information from just your first derivative. And so sometimes this added curve here, it's interesting, but it kind of makes it a little confused, and oftentimes on the AP you're only going to have this anyway. But this last little part here about your inflection point I do want to point out here. Okay, so I want you to write where f prime has a max and min, and in parentheses I'm going to say peak or valley, I'm going to switch to black here. F has an inflection point. Okay, and you can clearly see that right there. Okay. Now there's one other thing I want to go over, and that is when, instead of just peaks and valleys, what happens when your original function has a flat spot. And so I'm going to draw that on my last little section here, and we'll go through that one. Okay, now here is our third example here, where you will notice instead of having a nice easy peak and a valley, we have a peak and a valley, but we also have a flat spot, and you want to be comfortable with what that's going to look like. So let's just jump to what we normally know about our handcuffs with peaks and valleys and flat spots. So we go to our peak and all the way down here, and we know, again, slope of the tangent is going to be 0. A derivative is the slope of the tangent, so I'm going to have an x-intercept on the graph of my derivative. I'm going to go to this valley bottom right here. That one's kind of easy, same idea. But it's this one in the middle here where when you have a pause or a flat spot in the middle here, where you don't have a peak or a valley, we just have the flat spot. Well, you still have to account for it because you still have a tangent of 0. But it's the graph of the first derivative that's a little bit confusing. So we have our 3 x-intercepts, no problem. So the graph of the function is increasing, so just like the first two, we are positive. Okay. Now, between these handcuffs, I'm decreasing, and so I'm going to, my graph, this has to be negative. Okay, so far it's looking like what we did here, but here's the tricky part. Between these two, I continue to decrease. So in fact, I want you to look at what's going on between these two handcuffs. It is decreasing the entire time, interrupted by a pause. Well, if you have a flat spot in your original function, it's going to mean that your first derivative has to bounce or kiss off of here and stay negative before it then goes through again. So there's a really important connection that you want to make here. And that is flat spots on F. Flat spots on the original, flat spots on F create kisses on F prime. Okay, so there's our little kiss right there. And now as we continue, the original function is increasing, so we're going to have to be positive. So there is F prime. Okay. Now if we wanted, we can continue to the second derivative, but let's see what we can figure out based on our shortcuts from over here. Okay, so what I'm going to do is, let's say that's all they needed to know. They said, well, in fact, we could pretend all we had was red, and it said, what's going on? Where is the original increasing? And you could say, oh, well, where the original is increasing, wherever the derivative is above 0 or positive. So it would be in the first interval and the last interval, because it's decreasing in here, they're both negative. But then what if the question said, where is the original function concave up or concave down? This is where you want to go to this little hint right here. Where F prime has maxes and mins or peaks and valleys, the original function has inflection points. Well, look how easy this is now. I'm just going to go to my peaks and valleys. I'm going to say, oh, well, apparently, if I were to go up from there, I will get to an inflection point. And sure enough, I do. In fact, look at that. I'm concave down, and this goes to here, where F is decreasing, F is concave down, and there it is, corresponds. Okay, now where F is increasing, now I have another inflection point here. Now this overlaps with this flat spot right here. Flat spots are always inflection points, by the way, as well. And so you can see where F prime is increasing, I am concave up. Okay, so remember, this here is concave down to there. It's just this little interval here, it's concave up. Then it switches again, and notice now I have another minimum right here that is going to go up and be an inflection point on the original. And so this little part here is concave down because my derivative was decreasing. And then wherever the first derivative is increasing, I am concave up. Okay? So the actual need for the second derivative graph, you don't need it. And in fact, I encourage you to try to wean yourself off of it, but it's kind of nice to have that there. And so having these three, if you want to have a screenshot and print it or just recreate this, have this available for your test. It's really important. And so you just want to be very confident that the kisses here create flat spots. And by the way, because when they do derivative graphs, a lot of times you have to do integration and you're finding area under the curves. Sometimes the kiss is actually a harsh bounce, looks like absolute value, but it's a derivative function, so don't worry about it. It still does the same thing. Okay? So it doesn't matter if these were line segments or curved. You'll be set. So I just wanted to review this with you. And so take this away, add this to your notes as you're preparing. And we will see you next time. Thanks for watching.